are studying Zoll magnetic systems on surfaces, which can be seen as we will we'll see now as a very particular kind of integrable systems. And then from this very particular kind of integrable systems, what we want to do and what was the aim of our project was to deduce the existence of periodic orbits for perturbations of such very nice and understood situations. But before I start and go into the details, let me give maybe a rough idea of where the topics we are discussing today sits. So we can think of having here the set of Hamiltonian integrable systems. So some big set here. And usually what one does is to look at integrable systems which are non-degenerate. So here inside we have the non-degenerate ones. Meaning that the rotation numbers, the rotation number map, it's a non-degenerate map, so we'll induce locally some kind of diffeomorphism. And therefore, once I do a perturbation, I exit the realm of integrable system, and what I expect to find are many quasi-periodic motions via Km theory. Km theory. So we start with an integrable system where the tori have very different rotation numbers, and then out of these rotation numbers, then we find here the ones which are very irrational. But what I want to look at today is, in some sense, going in the opposite direction and look at very degenerate integrable systems. And these are, I will call it for the sake of today's talk, Zoll systems. So I have here Zoll ones. And by this, I mean, this other color, that all orbits are periodic. And form the trajectory of a free S1 action. Trajectories of a free S1 action, maybe up to reparametrization of time. So these are, in some sense, in this case, I have a lots of periodic orbits so everything is a periodic orbit in the non-perturbed case. And now I ask what happens if I perturb this situation. And so there are a lot of words going in this direction. And the expected thing, so there are many special results, but the rough idea here is that there are at least cap length of the orbit space. So here the orbits form an S1 action, so I can go to the quotient and look at the orbit space. Plus 1 periodic orbits. And there are many people who worked on such type of problems. I will mention here only maybe the most important one, Weinstein-Moser. Then you have Botkohl. And very related to the problem of magnetic systems, we have also here Ginzburg. But the list is not, doesn't end here. And so we see here that from Zoll systems, in some sense, I I go to a situation where at least some of the periodic orbits survive. So here one can also draw some kind of comparison between here a lot of quasi-periodic motion surviving, while here what we expect is just some finite number of periodic orbits still living. So today I'm going to restrict my attention to a particular class of Zoll systems by restricting here the class of Hamiltonian systems I'm considering. So today we look at the special class of Hamiltonian systems. Namely magnetic systems on surfaces. Magnetic on surfaces. And so we can think as magnetic systems as being a particular example of Hamiltonian systems, but on the other side, one can also think of them as a generalization, as we will now see, of standard geodesic flows, but also they are also generalization of geodesic flows. And so, as I said before, so for us the motivation is to find periodic orbits for such systems, and our strategy will be to understand Zoll examples in this class. So for the class of geodesic flows, there is a lot of literature on the subject. So it's also very easy to come up with examples of Zoll geodesic flows. So here, for example, I can say example is the geodesic flow of the round metric on S2. And the name Zoll comes from the first guy who studied more general examples of such systems in the realm of geodesic flows. And what I want to do today is try to find some non-trivial examples in the class of magnetic systems, and to see how the existence of this example is related to existence of periodic orbits, and of a very particular result in the existence of periodic orbits, which is the systolic inequality. So, and draw consequences on periodic orbits for such systems, in particular proving a local systolic inequality. Okay, so let me start then, after this introduction, with introducing these magnetic systems. And for the sake of today's talk, we will restrict our discussion to a very special type of surface, namely to the torus, so magnetic systems on T2. I will maybe say at the end what are the differences for the other cases. So on T2, and for the sake of notation, I take T2 as having two periodic variables, here x and y. And then for me, a magnetic systems will be given by a pair GB, where G is a Riemannian metric on T2, and B is a function, which I refer to as the magnetic function. And having such a pair, I can define a dynamical system in the following way. So a magnetic geodesic is a curve gamma from R into the 2 torus, which is parametrized by arc length, and such that the geodesic curvature of gamma is equal to B at the point gamma. So this is the geodesic curvature. And basically what I'm saying here is that this function B prescribes my geodesic curvature at every point. And one can maybe draw like what is the typical behavior of such curves. So if I have here maybe a standard geodesic, so this is a standard geodesic for G, so not a magnetic one, saying passing through a point xy with tangent vector v. Then I have to look at B of xy, and if B of xy is positive, I will have a magnetic geodesic going on the left side of my standard geodesic. So this is gamma if B of xy is positive, and on the other side, if B this gamma if B of xy is negative. And so what we have to think is that the higher, for example, B is, and the more wiggly our curve will be. So the behavior of our curves will be radically different from the behavior of a standard geodesic flow for G. And in the discussion, it's convenient to make some normalization. So I will write them here. So first of all, we can take the area, the total area, to be 1, and also the integral of my function B over the 2 torus to be non-negative. Okay, this is always, we can always achieve such thing by reversing the orientation of the torus or simply by scaling. Then what I want to say next is maybe the question that's it's more natural now is what I have to do such systems with Hamiltonian systems, and this is answered by looking at the lift of gamma on the unit tangent bundle. So I can consider the curve on the unit tangent bundle of the 2 torus. This is a flow line of or the trajectory of a flow phi GB on the unit tangent bundle, which is the restriction of a bigger flow, capital Phi GB, which is now a Hamiltonian flow on the tangent bundle of T2, where phi GB, this is a flow on the whole tangent bundle, and as a Hamiltonian flow with Hamiltonian the kinetic energy, the kinetic energy 1/2 p squared, and the symplectic form, which is the twisted symplectic form. Let me write it here. And symplectic form omega GB, which is the standard symplectic form, so px wedge dx plus dpy wedge dy, and then I subtract b times the area form of the base, so b the area of G. So this is, we can see as these systems as systems giving us the Hamiltonian dynamics at a fixed energy level, in this case the energy level 1/2 for this Hamiltonian. And so our goal will be then to understand the periodic orbits of phi GB. Okay, and here, so this problem has also a long history, and it turns out that we have to make a distinction between two cases. So the first case is when the integral of b is equal to 0. And this was tackled by Contreras, Macarini, and Paternine. And what they showed is that there exists some value, which is the Magnier critical value of the system, which is a non-negative number, such that if this value is less than 1, then there exists a periodic orbit in every non-trivial free homotopy class. Okay, and the second range is when this value is bigger or equal than 1. Then, in this case, there exists a periodic orbit bounding a disk, or a pair of periodic orbits bounding a cylinder. Okay, and here the disk and the cylinder are both embedded. So what can happen here is that either the orbit bounds a small disk, or you have here a cylinder bounded by the two periodic orbits. It's gamma 1 and gamma 2. Okay, and yes, so this maybe the fact that these two things are embedded doesn't follow directly from their paper, but from recent preprint from myself, Marco, and Luca. So this is the situation for the case the integral is equal to 0. Let me tell you what happens in the other case. So when the integral is positive. So here the situation is not as nice as this case here. So this is now the case where the integral is positive. And here the main result is due to Will-Murray, which showed that for almost, so let's say for a generic B, so not every B, there is a contractible contractible periodic orbit. Okay, but for example, in this case, we don't know if the orbit is embedded or not. And what we can say about both proof is that, okay, so we are in the we are working with Hamiltonian systems, so the proof use some variational principles. So proofs use variational principle. And in this case, the action functional, or at least one of the possible action functional, has the following form. Is the difference between the length of the curve with respect to the metric G and the integral of B over a disk bounding gamma. So if I have my gamma, which is a contractible curve in my torus, so this is my gamma, and then here I have my disk T2 of gamma, and then now a combination of the length of the boundary and the integral of B on the disk will give my action function such that the critical points of this guy are exactly contractible periodic orbits. And this is in the case, actually, in the case where the integral of B is equal to 0, there is another way to define the function such that it's well defined on every free homotopy class. Okay, so proofs uses variational principle, so one can also say something more about the index of these orbits. So in this case here, the orbits are actually minima. So here index is 0. Say here, here we have index 0. While here, this theorem is obtained by doing some minimax. So here, the index is 1. So meaning that it's made through a minimax family of dimension 1. So it's maybe the periodic orbit is not non-degenerate, but in some sense the expected dimension here is index is 1. Okay, so this is the what was known, and then now the question is if we can remove this genericity assumption there. So the question is, does there exist contractible periodic orbit with index 1 for all B with positive integral? And so the first step in this direction is using this perturbative result, which I described before by Weinstein, Moser, Botkol, and Ginzburg. So yes, if we are in the perturbative regime, let's say, meaning that either my GB is C3 close or C2 close to a Zoll one, or second thing is that GB is strong. So let me define what it means to be strong. So we say that GB is strong if I can write B as a constant S, positive constant, times a positive function, B1. So here B1 is a positive function, and S is a positive and constant, which is large with respect to G and B1. So what we have to think about is that in this case my B is very large. So what I see is that if I start here at a point xy with some direction v, then my orbit will wiggle very fast. And so when I take the limit as s goes to infinity, and I reparameterize my flow at the same time, what I see in the limit is that my point will stay fixed, and the tangent vector will simply rotate in the fiber. So something like this, no? Which is a type of Zoll flow on S of T2. So we can see that also in this case, in the strong case, our system is close to a Zoll system, even though this system here is not really a magnetic system because every point stays fixed. So in these two cases, we can use this perturbative result to find these periodic orbits. And now what one can ask is actually is if these orbits that we find can also be described in some way in terms of this action. So if the orbits that we find satisfy some relation with respect to the action, and this is what we are going to do now in the second part, which is about the local systolic inequality. So here the question is the periodic orbits, or do the periodic orbits, what can be said of LGB for periodic orbits in the perturbative regime. And so for this, we proved a result with Jiangsu Kang already some years ago, saying that now if GB is in the perturbative regime, then I can estimate the infimum of the action among all contractible periodic orbits with index 1. By pi over the total integral of B. And the equality holds with equality if and only if GB is also Zoll. Okay? So here actually we need a bit more. We need a C3, a perturbative regime in the C3 topology, and also here then this the fact that S is big with respect to G and B1. Here also we have to take this C3 topology, and so this in particular to prove this result, we use the perturbative result by Botkol and Ginsburg, but also you see that already having this result tells you that this set here is not empty, and so already here you have encoded the fact that there exists a contractible periodic orbit with this property. So once we got to this point, so our question was, can we go beyond the perturbative case? So can we prove systolic inequality if we are not in the perturbative case? And following some recent work by Umberto, Riniewicz, Abbondandolo, Bramham, and Salomao, we started looking at cases where we have some kind of additional symmetry. So we relax the perturbative condition, but we put into the picture some kind of additional symmetry. And so this is what I want to do now, so to look at this systolic inequality in the presence of some additional symmetries. So Umberto and collaborators, Umberto, Pedro, Alberto, and Barney proved a very nice theorem where they established this systolic inequality in the case of the sphere for geodesic flows. And so our goal was to try to see if their result would apply also in the case of the torus. So remark, so look for systolic inequality for outside the perturbative case. And requiring some additional symmetry. So this was one thing. It was kind of our motivation after proving this result. Another thing that I will discuss in the very last part of the talk is to, in some sense, prove that actually we have some kind of abundance of Zoll pairs, because from the way this result is stated, so we can very well imagine that we have a lot of strong pairs. So here you just take any positive function, and I will choose some S big enough. So we have a lot of examples in this class here, but for the first case, it seems so we didn't have many examples. So there is a very trivial example of a Zoll pair where you take G0 the flat metric and B0 constant, but apart from that, nothing was basically known. So the second thing which is left open by this theorem is to look for examples of Zoll pairs. Okay, so in the last part of the talk, I will try to address these two points. So let me start with the first one. So we consider now some kind of symmetry in our system. So we take as G a warped product matrix, so dx squared plus ax squared dy squared, and with B we take B of x, depending only on x. And for the sake of notation, I will denote by lambda the integral of B over my manifold. And now in this case, there is the multi-valued first integral. Which I will denote by I. So this is a function which has as domain the the unit tangent bundle, and is multivalued in the sense that it takes values in the circle, basically in the numbers with period lambda. And in order to write the function, let me write the unit sphere bundle as a product, okay, where we have here x, here y, and here theta, where theta is the angle of the tangent vector with the horizontal direction. So if this is v, then here we have theta, and this is the direction, the horizontal direction. So with this convention, then the function I, as a very simple form, is sinus of theta, ax, minus capital B of x, where capital B is a function from r over z into r lambda over z, with the property that the derivative of b is equal to a times b. Okay, so if you integrate then this function from 0 to 1, you just recover the integral of b. So we see that then this function, capital B, has exactly this periodicity here. So this is then our first integral, and then we have we want to study the foliation in invariant sets that this integral gives us. And for this, the first thing is to understand the critical points, the critical values of I. So we know that I is sandwiched between these two functions. One is I plus of x, which is a of x minus b of x. And the other one is I minus of x, which is minus a of x minus b of x. And then one sees easily that the critical points of I are basically the critical points of this function and the critical points of this function put together with the, in this case, you have to put as theta minus pi over 2, and in this case, plus pi over 2. So you have critical, then, so the y coordinate is free, and then as theta coordinate, you have minus pi over 2. And then here, plus times r over zeta times pi. Okay, and then for each of these two types of critical points, one gets periodic orbits which runs vertically. So if this is here my torus, then for the first type of critical points, I have orbits going in this direction. And for the second type, I have orbits going in this direction. Okay, so in this case, there are a lot of different phenomena appearing for different kind of set of critical points. So what we did, and we started to look at the case where the set of critical points is empty. And so this happens exactly when AB is bigger than the modulus of A prime. And this can be also understood in terms of a quantity called the magnetic curvature. So if the magnetic curvature is positive, then we have this condition. So this is the magnetic curvature, which we can think of this quantity as an analog of the Gaussian curvature for geodesic flows. and basically is defined as the standard Gaussian curvature. And then comes two terms depending on B. So the first term is B prime of x sinus of theta with a plus. And the second term is B squared of x. Okay, and then also this, in this case, this is easily seen to be minus second derivative of A divided by A. So, right. So we have here also this very nice characterization, one implication at least of having no critical points. And then, in this case, what we could show is that the systolic inequality actually holds. So here is a theorem with a cell and myself. So if then systolic inequality holds. And so, in general, we don't we don't know if the systolic inequality holds. And already to prove that there exists one contractible orbit, it's also kind of if there exists one contractible orbit, so this is also a non-trivial task. So we are working on this right now, but already this first step is not really immediate. And here the idea of the proof is that then one can consider a return map, because under this assumption, I know that, so the idea of proof is that you can consider here R over Z times minus pi over 2. Inside here, this is a global surface of section. Okay, and then also the return map is also easy to write. Return map is x, y going to x, and then some f of x plus y. Also for this kind of maps, it's almost immediate to show that the systolic inequality holds. Okay, so this was what I wanted to say about the first point. So in the last 13 minutes, let me give you an example of a Zoll pair, which is not trivial. So here we have an example of a non-trivial Zoll pair. So the idea is also to work with symmetric systems, but we will restrict our systems even further. So we will take as G a flat metric system, and then as B, we take this B equal to B of x. And now our equation of motions are x dot cos theta, y dot sin theta, and theta dot equal to B of x. And in order to have a global surface of section, we will assume here that B is always positive. Okay, so then what is the idea? The idea is that we start with a point here and shoot our magnetic geodesics in the downward direction, and then we get, after a certain point, a direction which points upward, and then we measure this delta here. So I have here a curve. This is a magnetic geodesic gamma, and let's say that my curve gamma has some first integral I, and then I can see this delta as a function of this integral I. So I can say that GB is Zoll if and only if delta I is equal to 0 for all I in R over lambda over Z. So basically what I want to show is that this function delta is the zero function. So, zero function. Okay, and so the idea now is to compute this function and basically to compute the Fourier coefficients of this function over here and then get some kind of condition. Okay, so what is then delta of I? So delta of I is the integral between pi over minus pi over 2 and plus pi over 2 of dy d theta in d theta. And now I can show this y dot d theta. And now I can substitute using the equation of motions. So this is minus pi over 2 pi over 2 sinus of theta. And here comes b of x of theta. And now I can remember I have this first integral I. Maybe I write it here one time more. So this is, in this case, is sinus of theta minus b of x, because this coefficient a was equal to 1. So I can now get x from this equation here. So here I get that x is b inverse of sinus of theta minus I. And so I can use this to substitute it here, and then I get sinus of theta. And then here times a function, let's call it c, of sinus of theta minus I d theta, where this function c of, let's say, u is just, it's just 1 over b of b inverse of u. Okay, so I'm satisfied with my formula for delta, and then now I want to impose that for all integers, the Fourier coefficients of delta is equal to 0. So what happens? So the Fourier coefficient of this guy is 0 to lambda in di, and then right, so here comes e to the minus 2 pi m I over lambda I times delta of I di. So let me substitute here and then exchange the order of integration. So what I get is d theta sin theta, and then here 0 to lambda, 0 to lambda, and then it comes c of sin theta minus I e to the minus 2 pi m I over lambda I. Right. Okay, now I make this substitution. Let's call this j. And if I do that, I get now that these two integrals decouple, and then I get minus pi over 2 d theta sinus of theta times e to the minus 2 pi m I over lambda sinus of theta. And then what remains here is integral between 0 and lambda of c yacht e to the 2 pi m lambda yacht d yacht. Okay, so this is then the Fourier coefficient of c minus m. So what I find now is that basically I have the product of two numbers, and this product has to be 0 for each m. So this means that one of these two numbers has to be 0, but one of the two numbers actually doesn't depend on my problem. So this number here is completely independent of my problem. So d theta sinus of theta, and then here e to the minus 2 pi m I lambda sinus of theta. Right, this, and then here comes this guy. And then, so if you put this number into Matemática, what you find is that this is the first Bessel function. Evaluated at 2 pi m over lambda. So this is the first Bessel function. Okay, but so here the moral is that if this number here was always different from 0, then in order to get something equal to 0, we are forced to take this c as a constant. And then basically this tells us that we don't get anything new. So we get just the constant b, which we know that it's a solution. But now every time this 2 pi m over lambda hits a 0 of the Bessel function, then we find some non-trivial c, which then for each epsilon we get here a value of this function c. This is this is 1 over lambda minus cosinus psi k psi k u over psi k. Let's go back. And then, right, so here epsilon here. And in order to, so here we know that this c has to be positive. So here the values of epsilon that are allowed are actually what is this? So this is psi square of k divided by lambda, but then I'm surely forgetting some 2 pi here, I think. See the formula. Yeah. Right. So this is correct. Like this is correct. Yep. So here it means that k over lambda. Yeah, that's correct. Okay. And then for each of these values of epsilon, then I can reconstruct my b from this equation. So in the last 2 minutes, I will show you some pictures of what you can put in a computer and what kind of curves will pop up when you use this recipe. Yeah, 5 minutes? Okay. Good. And right, thanks. Okay, so this first slide is just to recap what we have done. So we took the flat metric with the function b, which depends only on x, and is positive. And then we just set lambda to be this integral. And then my first integral is sinus of theta minus b of x, where capital B is now just a primitive of a small b. And then we took psi of k to be the k positive 0 of the Bessel function J1. So this was this condition that we got before. And now if we parameterize our x and y solutions with respect to this theta, then we get this, this formula that can be given to a computer to draw for us. And also, it gives us some kind of almost explicit expression for capital B. So what is explicit in this case is just the inverse. So, and then we have this equation here that we have to invert to get the real capital B, and then also the real small b. And when you see what we have done, so this m actually doesn't play much of a role. So if we take some finite cover of the torus, then it's just like divided m by what we want. So we can assume m equal to 1. And then now the relation for lambda is that lambda is equal to pi over psi over k. And this means that now my I was taking values in these circles with period lambda, which in this case is 2 pi over psi of k. And this epsilon was living in this interval, psi k over lambda, which when I insert lambda is just this interval depending on psi k. So I can then plot different curves for different values of the of k. So here this is for the first 0 of the Bessel function. So in each of these graphs, I have put a fixed epsilon. So in the first is always epsilon equal to 0, which corresponds to a constant magnetic field. So these are all circles with some radius. And then I start switching on this epsilon. And I can do so until I get to this critical value here. And basically what happens at this critical value is that the curves start having points like here where the my b is plus infinity. So they have some kind of edges. And so if I go, I cannot go then beyond these points. But apart from this, these are all kind of curves with b positive. So these are all kind of convex curves. And then as soon as I increase my k, I will get curves with more and more kind of edges. Also, before there were kind of just one edge or maybe two if I was in the green in the middle. And then here I start getting more and more edges. So this is for k equal to 2, 3, 4, 5, and 6. So they, and yeah, so as soon as, so if you go up, then the things becomes not very, so this is basically already for these first 6 values, you get an idea of what's going on. So some curves will become more elongated, some curves will become more short. But this is basically what happens if you do this with Python for higher and higher values of k. Okay, so thanks for listening.